So I couldn't even access it yesterday. It just said
You could
video.
not access?
It said video was private.
Oh, shit.
Sorry.
Sorry.
I thought I tried to, yeah.
Well, I can fix that.
Brilliant.
Probably something with the stream settings. We still have some time. Cool. Right. Oh yeah, it says private. I don't know why. Anyways, it's public now.
Brilliant.
Can you check
I'm just
it?
gonna go make myself a coffee. I'll be back in 5 minutes.
Yeah. Okay. Sure. Makes sense.
So it's the same link, just now public, right?
It is. Yeah. Nothing changed except that you should be able to access it now.
Yeah. It's looking more realistic. Yeah. Okay. Right. I'm just going to mute myself and have a listen.
Okay. Okay, I guess we should talk. How are things, Alex?
Well, now that you're not here, it's just all very bad.
Yeah, I see that you're very grumpy, like this dinosaur and his thing.
Yeah. It's just like I don't have my weekly meetings anymore. It's just there's nothing to look forward to.
Yeah, things are falling apart. I hope that at least you go climbing.
Oh yeah, I went climbing yesterday. I mean, that's not a problem.
Okay, then life is not so bad.
Yeah, that's pretty good. But I couldn't go climbing last week, which was bad.
How come?
I hurt myself, so I was.
How did that happen? Not during climbing.
No, it wasn't climbing.
Of course not.
I was lifting something and it hurt my back, so no climbing.
Oh my gosh, you should never do anything else but climbing.
That's what I was thinking. Because like I was doing this these calculations, and I thought this is dangerous because if I hurt myself, like my hand.
That sounds all good on YouTube.
Yeah, sounds good.
How's
Awesome.
the UK been? Oh.
Hmm?
Oh, I thought we were still talking. Never mind.
Yeah, so you're in London.
Oh, I am. Yeah.
Great. How's it going?
Yeah, good. Weather is nice, as you know. I don't know how far we are from each other. It's
Are you in the Google offices?
But it's
I'm at my flat, so we live quite far out of London, like zone 2, zone 3.
Are you going to the uni?
Yeah,
sometimes?
Once a week sometimes, yeah.
Once a week.
I mean, I could come in more, but I'm lazy and I don't like, well, I like cycling, but I often, if it's raining, I'll often work from home.
So far this week was awesome. Hey, Gaga.
What's up? Yeah, sorry I'm a little late. I'm in Amsterdam for a real work trip and all that.
The reshuffling of everyone.
All right, so let me upload the slides.
Good. Oh, and
Did you already do like the YouTube?
Yeah, we
Madness?
did that, and it's all fine now.
Okay, thank you.
I can see that there is an excellent connection, and all is fine.
Somehow your sound is not as good as usual.
Oh no! Wow, I didn't do anything with it.
No,
Oh,
I guess
my
your
sound,
headset is
my,
different. Yeah.
yeah. So it's like these are earbuds, right? So they're not equivalent to the setup I have at home. But wow, maybe I just keep quiet.
Not too horrible.
Okay.
Right, I'll put the slides in.
So how is life in Berkeley, Martin?
I guess I was saying it's a little chaotic. At least we've ended fire season, but we've had kind of torrential rains.
Oh yeah, I've
Everything's
heard about it.
it's just very extreme. Everything. It's I don't know. It's like it's either incredibly hot and smoky with fires, or it's like raining and cold with mudslides. So
Yeah, but the rain is over now, right?
the big one is over, although it's still raining this week, but
Oh,
sort
okay.
of gentle rain. I mean, we desperately need it. The entire West Coast obviously needs it. So
Yeah. Maybe it could have come a little bit slower and smaller pieces.
Did Alberta get hit by all the fires in Oregon and so on?
Fires not in Oregon, but like we had our own fires, and we got fires in Saskatchewan. Like everything was on fire. It seemed like BC, Alberta had its own fires, and like it didn't. It seemed that it's not going to matter which direction the wind blows. Usually, you're like, oh, if the wind doesn't blow from that direction, we're not going to get the smoke, because in Edmonton itself, usually, like there's no fire there. But yeah, not this summer. It wasn't that bad. So usually it was like some smoke in the air, but it wasn't as bad as like a couple of years ago when it was really bad there, in San Francisco. I remember visiting and wasn't able to even get out on the street. So it wasn't that bad, but we still had our own fair share of fires. Yeah, and they say, well, the fall, I cannot complain about the fall. The fall was beautiful and really warm, and we didn't get snow yet. But they said that for the winter, the snow is coming. It's going to be huge.
Are those which mountains are in your background picture? Speaking of snow,
those are actually the mountains in Alberta. It's called Heart Mountains. It's near Canmore, which is near Banff. Yeah.
Okay, yeah. So just en route to Banff.
Yeah, that's right.
Are you a winter sports person?
Both summer and winter. Try to staying on the top of things. So winter it's skiing, and summer, I don't know, climbing and biking, sort of thing.
You trad climb, or like you're scrambling, or trad?
Well, scrambling as well, but yeah. No trad is allowed by the family's order.
Yeah. The Rocky Mountains, the rock condition is so crazy. I find it very scary, having sort of been used to solid granite all the time in Yosemite and surroundings.
You have to be very careful.
Yeah.
Wow, when the big piece comes out. Scary moment.
Yeah.
Well, if you're doing sport climbing, then it's a little bit different, because then usually that rock has been tested and it's pretty solid. So I don't think that that's too dangerous, or it would be much riskier than elsewhere in the world. But definitely, if you're doing trad, then you have to be super careful. I watched a video though about some people climbing some mountain in Sweden with ropes and whatnot. So it was proper technical climbing, and there, so there the rock was just falling on its own. How do they do this?
Yeah,
It makes no sense.
it's the risk is too uncontrolled.
Yeah, they still went up. They were like, oh yeah, it's just like a rock of the size of a school bus just came off the mountain. We heard it was really loud. It's really scary, but we still go up. Okay. Not me. But so it's bad, but not bad, I think. Scrambling is good. So I take that you yourself climbed.
Mainly these days I'm just doing lots of scrambling, some gym climbing, but yeah, nothing. I have 3 kids, so I just really don't have time for.
Well, you have
much.
to take the kids as well.
Yeah, they're not old enough though. Well,
Okay.
one of them is a climber, but I have 2 twins that are just 3. So.
Yeah.
You know.
Okay. Well, you can take them to the playground for little things.
Yeah, actually, they're starting to climb, and one of them is actually quite good. So.
Yeah.
Like strength to weight ratio is off the charts. So.
Yeah. And finger strength. I mean, that's incredible. Yeah, with little kids. I remember my son, when he was around 3, we went to a coffee shop, and we put him like on a chair, and he was sitting there and was supposed to wait for us. And I go and pick up the order, and by the time I look back, he's hanging from the table with the finger. He was just like peacefully hanging there.
Well,
what happened there, dude?
You've got to get your fingerboard training in when you can.
Yeah, the coffee shop is the best place for doing that. Okay.
Somebody's asking about the slides. I emailed you guys the slides about 9:30.
Yeah,
so
I think the link should be made available here.
Yeah.
I think we should also start probably.
Yeah, I'll take care of the link. I'm going to post it in a second.
Yeah.
Let's see, people.
Okay, I can start sort of a general introductions then. So, hi everyone, welcome to this week's seminar. I hope you all, well, if you're watching, I guess you will manage to figure out all the time zones, and if not, well, it will be on YouTube, so hopefully you can catch up then. I think lots of you will have been here before. You sort of know how this works. We'll have a talk of approximately 50 minutes, and then 10 minutes for sort of more on the record questions, and then we will turn off the recording and you can ask any of your more controversial questions, anything you didn't want to ask while being recorded. Please, while the speaker is speaking, make sure you're muted so we can hear him. If you have any questions, put them in the chat and we can attempt to answer them, or we will pass them on to the speaker at an appropriate pause point. That applies whether you're watching on Meet or on YouTube. And I think that's everything. Can we start the recording? And over to you to introduce the speaker.
Gaga, you're muted.
Oh, am I supposed to? I thought that you're doing it, Chava, no?
Oh, okay, sure. Okay. Sorry about that. Yeah, so it's a great pleasure to have Martin here. I know Martin from his many papers and books as well. And I've been an admirer of his very thorough work and very pointy questions. And I'm a big fan, so it's really a great pleasure to have him here. Of course, he has won many awards and he has been decorated in so many different ways that it's really hard to go through that. But I think for us, it's like, it's super exciting to have him. So I think that without any further ado, I give the stage to you, Martin.
Thanks so much, Csaba, for the kind invitation, and thanks to you and the other organizers, Chiara, Gergely, Alex, for running this seminar. It's great, and it's a pleasure to be here. This is going to be some joint work with some colleagues at Princeton, with Yaqi Duan, who I think is actually here, so she can answer any of the tough questions, and Mengdi as well. And these are Slack avatars. Yachi's Peppa Pig, Mengdi's a cute porcupine. So when I work with people, I have my daughter, my 8-year-old daughter, 7-year-old daughter draw some Slack avatars for them based on their choice. On the other hand, I don't have a choice. I'm known by my daughter as Grumpy Dinosaur because she said, "You are old and you are grumpy." So can't argue with a 7-year-old. All right, so I'm going to be talking about policy evaluation in non-parametric settings. Maybe just a few high-level words. I'm a relative newcomer to RL, and so still busy learning from all of you in the community. To be honest, I've sort of been a closet lover of RL my entire career, but I didn't really feel brave enough to work on it until relatively recently. I think RL is fascinating because it combines so many different things. It has decision-making, has active versus passive learning, it has dynamics, it has non-parametrics. So I think it's a really wonderful area to be working in, and obviously has lots of exciting applications too. So let me just give you the broad motivation for the kind of work that I'll be talking about here, and also the kind of work I think many other people are doing. I'd say broadly, at least from my perspective, we've seen a lot of advances in applied RL, but theoretical understanding, there's still a lot of very interesting gaps to fill in. So on the positive side, as I said, empirical successes, that's a big positive. Something that's sort of interesting is that algorithms in practice are behaving a lot better than existing theory would suggest. Sometimes they're working in situations where a worst case analysis would say nothing should work, or sometimes they're working where there are polynomial time bounds, but they're working much better than what a current analysis would imply. So I'll talk a little bit about sort of the notion of instance dependence in RL, which I think is an interesting and exciting area. So the sort of broad motivation for this talk is to try and provide theory that's more reflective of empirical behavior. I would like theory that's accurate enough to actually predict what happens on particular problem instances in a quantitative way. So I hope you get a flavor of that kind of result from today's talk. Okay, so for this audience, I don't think we need to spend too much time on the basic setup, but let me just set notation so everyone's on the same page. So we're looking at an MDP that has a state space X, an action space U. We have a family of probability transitions, and I'm going to be looking at the discounted setting. We have a discount factor, and we're looking to maximize an expected sum of discounted rewards. So it's just the standard classical discounted MDP. I'm actually in today's talk going to be interested just in a simple problem, namely policy evaluation. So we're going to fix a policy, a mapping from states to actions. And the problem I'm interested in is just methods for estimating the value function for that policy. Okay, so that's pretty simple, but of course it's sort of a core subproblem that underlies many other things that we do in reinforcement learning, for instance, policy optimization and so on, policy gradient methods, actor-critic methods. Underneath them all are schemes that are evaluating value functions or Q-value functions. Okay, so the problem's pretty simply stated. We're going to look at a Markov chain. I'll assume that the Markov chain has a stationary distribution. It's ergodic and so on. And basically what we're trying to do is compute a fixed point of the Bellman evaluation operator. Right? So this operator is a mapping on L2 mu. That's the space of the L2 space equipped with mu as the underlying measure. And what it does is, if you give it a function in that space, some value function, it maps it to a new function that, when evaluated at x, takes the reward function plus this integral here, this conditional expectation of the value function evaluated at the next state. So throughout the talk, x primed will always be next state, x will be current state. Okay, so what I'm interested in today is I'm interested in sort of non-parametric settings of this problem. If you have a tabular problem, then this is just basically a matrix. It's a linear system of dimension as many discrete states as you have. It's more interesting, more challenging when you have continuous states. So the value function is, something on something defined on a continuous space L2 mu. So in this setting, even if you knew the transition, this transition function, that's not the setting we're considering today, but just to be clear, even if you know that, computing the fixed point of this integral equation is not actually trivial. And there's sort of classic work due to Chow and Tsitsiklis and a nice paper by Rust from the 90s studying this particular setting. In the RL setting, what we're talking about, you of course don't know the transition, but you have available samples, x primed, state and next state pairs, along with noisy observations of the reward. So in this talk, I'm going to be considering a very simple observation model. There's nothing off policy. There's nothing about exploration. We're just going to be looking at a model where you observe IID triples of x primed, and Rx pairs. And we're going to analyze the behavior of a particular class of kernel methods in this context. Okay, so in general, it's not possible to solve that equation exactly. And so you, of course, have to start searching for approximations of the value function. The simplest idea that you might have, and something that's, of course, very well studied by this point, is that you would define some collection of features. So you can think about a feature map that takes states and maps them to a d-dimensional vector. So you have d features in this case. You look at linear expansions of these features. So you get weights theta j, one weight for every feature. And you look at the linear class formed by all possible such weighted linear combinations of features. Okay, so this is, of course, what methods like LSTD and TD and so on are doing. Just so you have the geometric view of what's going on here, because it's relevant to what I'll be talking about later. Geometrically, what's going on here is that methods like TD and LSTD, if we think about them at the population level, that is, if we think about them when you have infinite data, what they're trying to do is they're trying to find what's known as a projected fixed point. Okay, so this is a projected fixed point. What is a projected fixed point? So we have a linear space of functions. That's in this diagram, this space here. We have a projection operator. We're projecting under L2 mu. And so if you give me some function, for instance, Bellman applied to G, I can always project it back to the linear space. And the population level LSTD fixed point has this very magical property. The magical property is if you start at the fixed point and you apply the Bellman operator, you go outside the linear function class in general, and when you project back, you magically end up where you started. Okay, so that's very special. In general, if you apply the Bellman operator to some arbitrary function, you're going to go somewhere else and project back to a different point. Okay, so that's the LSTD fixed point. Bertzikas in particular sort of has very nice views, in my opinion, of this kind of geometry that I've learned from. And also, just historically, it's interesting to know that, of course, in RL, this idea goes back to Rich Sutton, his seminal work. But more broadly, the idea of when you're trying to solve fixed point equations with operators, this idea of looking for projected fixed points actually goes back to work due to Galerkin for solving PDEs. So this idea of sort of searching over subspaces for approximate fixed points is a pretty general and powerful one. Okay, so those are linear approximations. What I want to talk about today is non-parametric approximations. And of course, there's also a beautiful line of past and ongoing work here. This is only a partial list. Forgive me if I've excluded something that you feel is particularly relevant. What I'll be talking about today is this class of methods based on reproducing kernel Hilbert spaces, and I'll give more background on them in a moment. And there's been plenty of past work on them. Just to be clear, there's a very nice paper by Ormanite and Sen from 2002, which is about kernel estimators for fitted Q, but it's actually not reproducing kernels. It's for what are known as Watson kernels. These are certain class of smoothing kernels in statistics. The other paper that I'll sort of compare to, because it has some results for general non-parametric function classes, is this paper from 2016 by Faramond et al. I was sort of inspired by reading this paper. Okay, so what are reproducing kernels? Let me give you a little bit of background. So a kernel function here is just a function from pairs of states x and z. You have a bivariate function that gives you a real number for every pair of states. And you require that it's PSD, that means positive semi-definite. That's just a generalization of the notion of a PSD matrix to a function, to a bivariate function. Okay, so there are a lot of standard kernels that people use that are PSD. So the Gaussian kernel, right? This is e to the minus, for instance, 1/2 x minus z squared, perhaps with a bandwidth. The Laplacian kernel, this is also a translation invariant kernel. This Sobolev kernel is a little different, actually. Let's see if this works. This is the kernel minimum of x and z. This is what's known as a spline kernel. It generates functions that are Lipschitz, so sort of have one derivative in a generalized sense, but can otherwise be pretty non-smooth. The Gaussian kernel here, of course, generates functions that are, in general, very smooth, because the Gaussian is a very smooth function. Okay, so I'm putting these in 1D, but of course, you can have d-dimensional generalizations of all of these things for higher dimensional feature spaces. Okay, so if you've defined one of these kernel functions, then what you're doing, how you're generating approximations is by taking functions that are weighted sums of kernels. So what does that mean? It means that you're allowed to pick some positive integer, you're allowed to pick a vector of weights, and you're allowed to pick any collection of states. And then you look at functions, f of x, that have weights alpha I, but then kernel evaluations x and xi. You can sort of think this is the kernel, think about it like a similarity metric. It measures how similar x is to xi, and alpha I is a weight that tells you how much weight you want to put on that particular similarity measure. So in general, functions in H are weighted sums of kernels or limits of these kinds of things. You have to close the space. And the inner product, if you look at the inner product on the space, if you had another function that looks like a weighted sum of bumps, if it has some coefficients beta, so I have beta for G and I have alpha for F, then the inner product by definition is just this weighted combination alpha I bj with kernel evaluations at the relevant points. Okay, and this is why we need the kernel to be PSD, because we need the inner product to be well defined for it to induce a norm properly. Okay, so what are we going to do? Well, we're going to consider one of these Hilbert spaces, and as a generalization of LSTD, we'll do the natural thing. We'll consider a projected fixed point onto the Hilbert space. Strictly speaking, we have to close the Hilbert space in L2 mu to define the projection. That's a technical detail, but can actually be important. Okay, so what we're doing, if we had a linear kernel, then this is exactly LSTD. But we're going to be interested in general in nonlinear kernels, and many of them are rich enough that it's actually quite often the case it would be reasonable to say that the true value function is actually in your space. If the true value function is actually in the RKHS, then we will not have any approximation error. So, for example, if I took a spline kernel like this generates a pretty large class of functions quite quickly, because it allows for a lot of non-smoothness. So it's quite possible you do not have approximation error, but more generally you would have approximation error. Okay, but the geometric picture is the same. What I'm doing is I'm projecting, and I'm looking for something that satisfies this condition as before, except now I'm working with a general Hilbert space instead of just a linear space. Okay, so this is not a new idea, by the way. People have proposed this before, but I just want to set it up carefully so that we're all on the same page of what we are doing. Okay, so abstractly, we're looking for a projected fixed point, but we, of course, have to figure out how to do this on the basis of data. So let's first discuss what this fixed point looks like if you had an infinite amount of data. All right, so when you have a reproducing kernel Hilbert space, you can define two operators with it. In our case, we have samples state and next state. State is drawn according to the stationary distribution. Next state is drawn according to the transition. Okay, so you have the covariance operator, which acts on pairs of functions and computes their correlation or covariance when the functions are demeaned. And you have the cross covariance operator, which looks at the expectation of f at current state and g at next state. Okay, so these operators, of course, arise in LSTD. If you had a linear kernel, these are just regular covariance matrices or cross covariance matrices of your features. And what you can show is that the population level LSTD solution is a linear operator equation in terms of these operators. Okay, so what is it? The fixed point says if you apply the covariance map to f star is in the Hilbert space, you apply the covariance operator to the reward function, and then gamma times the cross covariance operator to f star. That's a fixed point. Okay, so that's just a generalization of what we know from LSTD. LSTD satisfies at the population level also a special case of this fixed point relation. Okay, so how do we estimate it? We're not doing anything fancy here. We're just going to do plug-in with a little bit of regularization. Okay, so in practice, we've got a bunch of samples. Sorry, I should also have xi primed. I have state, next state, and reward samples. So I can use my n samples and do empirical approximations of the covariance operator and of the cross covariance operator using my data. Okay, so those are empirical operators. I'm going to regularize the covariance operator, basically because you can see I need to invert it. So for statistical reasons, we're going to regularize it. And then I'm going to solve this equation right here in terms of these empirical operators that we can compute.
Can I ask a quick question?
Sure, yeah.
So you said that we need to invert the covariance operator, but It's not really a covariance operator that you need to invert. It's like the covariance operator minus gamma times the cross covariance operator that we would want to invert. So there is a small discrepancy there.
That is correct, yes. But yeah, so strictly speaking, yes, it's the covariance minus gamma times the cross covariance that we're inverting, but that definitely needs to be regularized. So yes.
Right. But that operator is like a really ugly one. It's not like a nice positive definite operator as the covariance operator. And so one wonders whether the regularization, as we usually practice it, is that really appropriate for doing this? It's just like a, you know, maybe a question that leads outside of the realm of the talk, but like I was wondering about that. Have you thought about it?
Yes, this plays an important role in our analysis. That operator is somewhat ugly, but the population level of that operator, concretely, I don't want that. Right, so we're talking about at the population level, this operator is an interesting operator, right? It's a little bit ugly, but I wouldn't say it's disastrous. For instance, an interesting property of this operator, and that's something that we use heavily in the analysis, is this. So if I look at this in the Hilbert space, so I'm looking at covariances and cross covariances, this is always bigger than or equal to 1 minus gamma times E of F squared under mu. So it's not PSD per se because it's not symmetric, but it does have this property, and this property is actually very important to us. We actually end up bounding many things in the middle of the analysis. We actually bound in terms of this object, and then very late in the analysis, we use this bound. And that bound can be weak, by the way. That's a worst case bound. If you had better mixing properties, you would have a better bound.
And so how does this relate to that you should be regularizing the way you're suggesting for regularization? Is there some relationship there? Maybe.
Let me maybe let me move on a little bit.
Sure.
I think we all agree we definitely have to regularize, and the choice of the regularization is going to be crucial, and I will give you a very precise answer for that question. Thanks for the questions. It's fun to be interactive. Okay, so this is our estimator. I guess to be more precise.
In the meanwhile, Parde was also trying to ask a question. I think he raised his hand. So maybe you can have a question too.
Hi, I have a quick question regarding the setting. So is xi prime the same as xi plus 1, or are each of these xi prime ri completely independent across I?
Anything with a prime throughout the talk is always a next state sample. So we're observing triples, x, current state, x primed, next state, and then reward function.
I guess the question is whether there is independence between the xi primes, and ri.
Across n, in this talk, across n, all samples are IID. So it's the sampling model is very simple, Triples, IID, n of them, As I'll mention at the end, we do have ideas how to do it in the Markovian setting, but everything I'll talk about today is non-Markovian. Okay. All right, so let me give you a theoretical appetizer. So as I just said, the sampling model is very simple, and the setup is pretty simple, to be honest. So I sort of feel like if you study a fairly idealized problem, which we are, then it's your obligation to give fairly precise results. If you study a non-idealized, quite technically challenging problem, then you can have a little more leeway. And what I'm showing you here is the comparison between what happens in practice on simulated examples that we construct versus what our theory predicts. And in particular, what I'm focusing on here, because I think this is something that's interesting and actually distinguishes this problem from a static prediction problem, I want to understand exactly how it depends on the effective horizon. Okay, so 1 over 1 minus gamma, that's sort of the way to think about the effect of the discount factor. So of course, in general, problems get harder as you increase the effective horizon. So what I'm plotting here is on the x-axis, increasing effective horizon. And on the y-axis, I'm plotting the mean squared error of this method. And what I've done is we've constructed 2 different ensembles. One is actually based on a Gaussian kernel. You have an exponential behavior of the eigenvalues that I'll talk about in a minute. The other is based on a Sobolev kernel. You have a polynomial decay. It's a much larger function class. So what's interesting here is that the theory predicts that there are particular polynomial functions of horizon. This prediction is, so the solid line is the theoretical prediction. Each one of these dots is the mean of something like, I think, 1,000 trials with error bars. Okay, so the theory is predicting very precisely what this method is doing as a function of horizon. And you can see a very big difference between the 2 cases. We also make a particular prediction for this polynomial function. I don't remember what it is offhand, maybe something like 7/5. Okay, so this is interesting because this cubic scaling that you see here, that's what is known and familiar from tabular and linear problems. But this larger function class, interestingly, has a much weaker scaling with the horizon. And the theory that I'm going to present will make it clear why. Once you see the theoretical results, that's not going to be surprising. But it is interesting to sort of see it up front, hopefully, so that your appetite is whetted for the results. Okay, so what are the ingredients in the analysis? So the first ingredient is the behavior of the kernel eigenvalues. So just a little bit of background. Under some regularity conditions, kernels have what's known as a Mercer expansion. That's what I'm writing here. It's really just a generalization of the fact that a PSD matrix has an orthonormal set of eigenvectors. It's a generalization in the sense that you have eigenfunctions, these phi-j's, and these are orthonormal in L2 mu. Mu, remember, is the stationary distribution. And then you also have non-negative eigenvalues, these mu-j's, and we're going to order them in this way. Okay, so what's interesting here is the following. How do these eigenvalues decay? So decay, I mean, when I start increasing the index, I'm ordering them from largest to smallest. And so what you can do is for various kernels and also for various choices of the stationary distribution, you can evaluate these eigenvalues. You can actually approximate them just by a Monte Carlo sampling procedure and computing eigenvalues of kernel matrices. So what I'm plotting here is index of eigenvalue. And on a log scale, also log index eigenvalue, I'm plotting the eigenvalue. So it's basically sort of a spectrum of this operator. And you can see interesting things. For instance, something like the Gaussian kernel is very smooth and its eigenvalues actually drop off quite rapidly. This is actually a quadratic drop off. It's actually looks quadratic on this scale, but it's actually an exponential drop off when you don't take logs. Something like the Laplacian kernel in red here has a much slower drop off. It kind of looks like this is decaying at a linear rate on a log-log scale. That means it's decaying like some polynomial in 1 over j, where j is the index. Okay, so you can get a very wide range of behavior out of these eigenvalues. And just to be clear, it also depends on the choice of mu. So for example, if I take the Gaussian kernel and I apply it to a d-dimensional problem with a distribution that puts mass basically everywhere in d-dimensional space, something like a full dimensional Gaussian, you'll get very slow eigendecay because, of course, the cursive dimensionality will start to kick in. But if you had a stationary distribution that puts mass preferentially in some smaller part of the space, that will actually change the eigenvalues a lot. You'll get much faster eigendecay. So you want to be clear that if you think about, adapting to problems in practice, high dimensional problems in practice, probably the stationary distributions quite often are concentrated on smaller parts of the space, and that will lead to more favorable behavior in these eigenvalues. Okay, so ingredient number 2, well, how do the eigenvalues enter the analysis? So here's a function that's known from past work. It's known as a kernel complexity function. Let me just roll up so you can see the references at the bottom. All right, so this function is, we'll call it the kernel complexity. Okay, so it's a function of some delta. Okay, that's the error level that we're aiming for. And what does this function do? It's pretty simple. It basically just says if your error level is above the eigenvalue, if delta is bigger than some mu j, then you pay a price of 1. Otherwise, you just pay a price of the eigenvalue over the error. So it's basically counting the number of degrees of freedom in the kernel, but counting them at scale delta. If you plot this function for a given kernel, you'll see something that looks like this. Okay, so this is for, I think, a Sobolev kernel. Okay, you can see that this is in general, monotonically decreasing function in delta. As you increase delta, clearly C of delta goes down. Now, what's relevant in statistics is solving a fixed point equation or an inequality that involves some measure of SNR. This is very, very important, and I'll talk a lot about it in a minute. And times delta. Here I've included square root n as part of the SNR as well. As n goes up, your signal to noise ratio will go up. Okay, and what this theory says is that the error that you expect to achieve from your estimator will happen at the intersection of this line, that's this line right here, and this function. So you're going to find the smallest point at which this inequality holds. And we'll prove guarantees that involve that number there. So what happens as you change your SNR? If the SNR of your problem changes, for instance, this number goes down, and I'll tell you in RL how this SNR depends, then the slope of this line decreases. It moves like that. This is a low SNR problem. And this fixed point moves along this axis. Okay, so that's telling you that if you have less signal to noise ratio, your error will be larger. Okay, so that's the basic geometry. The eigenvalues, which are determined by the kernel and the stationary distribution, sit here. And the mystery is, what is the right choice of this for policy evaluation? Just to be clear, if you're doing standard things like a static prediction problem, something like kernel ridge regression, this SNR is basically 1 over the noise that you're adding to your functions. It's 1 over the observation noise, which makes perfect sense. For policy evaluation, we have additional types of noise that are somehow more interesting than that. So that's what we need to understand. Okay, so here is the signal to noise ratio for policy evaluation. Okay, so it's a function of sample size. I'm going to lump in the square root n sample size here. It grows inversely with the effective horizon. So if your horizon is longer, your signal to noise ratio is smaller. It depends on the Hilbert norm. We're assuming this is finite. That is an assumption. The Hilbert norm of f star, the projection, minus the reward. And it depends on sort of a mean squared error of the Bellman error that you're making at the fixed point. So f star is the fixed point. Could be equal to the true value function, but it could be different in general. And so this is a form of error. And as that goes up, that depends on f star, what you're trying to estimate, your SNR will go down. So let me just actually unpack this. I think the Bellman error is possibly the most interesting things. The Bellman error, if you unpack it, has sort of two components. One is the squared Bellman residual. That's like a squared bias term, because in general, f star is not a fixed point of the Bellman operator. There could be approximation error. And then it has a pure variance term, the sort of variance that you see when you evaluate f star at next state, conditioned on previous state. You take that conditional variance and then you average it over the choice of state. Okay, so if you don't have approximation error, then this term is 0. And you're dealing purely with this object, which makes sense. But in general, you have both sources of error that are sitting inside this quantity. Okay, so that's the SNR. Hopefully it's sort of intuitive the way that different parts are behaving. And here's a theorem. Let me maybe just scroll to the full slide and walk through it slowly. Okay, so the theory is telling us something about the kernel LSTD estimate. And if you remember, that estimate was actually a family of estimators that depended on this choice of this regularization parameter right here. Okay, and so what this theory is saying is the following. It says, as long as you choose lambda n big enough, and big enough means larger than some, anything like C0 or C1, these are just universal constants. They don't depend on anything about the problem. So bigger than some constant times this critical radius, which I'll unpack in a minute. And this is quite interesting, times 1 minus gamma. This is something that you never see in a static prediction problem. So if you choose it large enough, then with high probability, the L2 mu error in your estimate, so this is the kernel LSTD fixed point. That is your estimate. It depends on n and lambda n, will be less than or equal to a certain radius squared. The radius is defined right here. The radius has this term involving the Hilbert norm that we saw before, has an additional term involving a soup norm for technical reasons that I can get into. So a radius squared times this critical radius times lambda n divided by 1 minus delta. Okay, so what this says is that if you choose, it doesn't tell you anything if you choose lambda n too small. But if you choose lambda to n too small, basically the method's going to become unstable and you'll get a very bad blow up as a function of lambda n going to 0. What it does say is that if you choose lambda n large enough, then you'll pay a price that's proportional to this critical radius plus lambda n divided by 1 minus gamma. So if you choose lambda n too large, you actually are going to over smooth. You're going to get too much bias in the estimator. But if you choose it just right in the Goldilocks sense, then you'll get lambda n over 1 minus gamma to be of the same order as this. Okay, and what is this critical radius? Well, it's the solution to that inequality that we saw on the previous page. As I'll discuss towards the end, in practice, you cannot just immediately solve this equation because not everything in this equation is known, but I'll sort of discuss data-dependent ways in which you might approximately solve this equation. Okay, so that's the main theorem that applies to a pretty general class of kernels. There's a few additional assumptions here, technical things that I'm happy to get into if people are interested, but just wanted to keep things simple so the main flavor of the result was conveyed. Okay, so that's a general result, but we can get intuition for it by unpacking it in particular cases. So let's start unpacking this result. Probably the simplest case is if you have a linear kernel, so you're just doing LSTD. Okay, so you have a linear kernel function on the feature space. It's not purely linear, it's linear in feature space. And if you unpack all the ingredients of this theorem, what it tells you is that the error is going to scale like this. You're going to get that squared Bellman error that I defined before over 1 minus gamma squared d over n. All right, so that's exactly what you'd expect, because in LSTD with d features, a d-dimensional feature map, you have d degrees of freedom. This is acting like the effective noise, because as the method proceeds, it's getting very close to this point, and these are the fluctuations that matter. And you do pay something in 1 minus gamma squared. Okay, and so the worst case of this, just for people who understand all the scalings, the worst case scalings with gamma, in the worst case, you can make this quantity, in the worst case, can behave like 1 over 1 minus gamma. Okay, and in that worst case, you will get a cubic scaling here, which is what we know from worst case analysis. So that makes sense. So this result, give me a sec. Of course, past work on this topic, lots of it. This result kind of sharpens some results from this paper. But this result is actually not as sharp as results from another paper of mine with collaborators, but only applying to LSTD. There's more going on with LSTD than this result applies. But I think it's useful to understand when you have a general result, what happens in concrete cases. So that's one concrete case. So that's interesting, but it's not really non-parametric. Let's look at something that is actually non-parametric. There are many kernels for which the eigenvalues have polynomial decay, for which there's some alpha bigger than 0. And the eigenvalues, as you sort them in terms of the index j, they decay like j to the minus 2 alpha. So things like spline kernels, Laplace kernels, inverse inner product kernels, I think something like the neural tangent kernel, all of these have this kind of polynomial decay. In high dimensional problems, it's possible that alpha can actually depend on d, but nonetheless, they are of this family.
Can I ask a quick clarification question here?
Sure.
I saw that these eigenvalues depend also on the distribution mu.
Yes.
So then, how can we say that, like, if you take a generic kernel, then are you saying that no matter what mu is, the decay of the eigenvalues are going to be such and such? Is that what you're saying?
No, yeah, sorry, you caught me. I'm being imprecise. So these examples that I'm giving are, for instance, with spline kernels, if you take the uniform distribution for a spline kernel, and it's a spline kernel with smoothness alpha, then a uniform distribution will generate this eigendecay. But you are exactly right. Like I was saying before, if the stationary distribution is very different than uniform, you might have even faster decay.
Right. Okay. Yeah, understood. Makes sense. Fine.
I think that point is actually very important because, you know, generically, if you look at high dimensional problems and you have high dimensional distributions with no structure to them, you're going to get an exponent, you're going to get some cursive dimensionality in the behavior of these eigenvalues. There's no free lunch. But I personally think what's going on in practice in a lot of high dimensional problems is that the stationary distributions are interestingly concentrated, and therefore you must get much faster decay than sort of a worst case guarantee would imply. That's vague intuition, but that's my intuition.
All right. Okay.
Okay, so what this result says is the following. It says in this case, the delta squared is more interesting. Okay, so what happens? You get this Bellman error term here on top, 1 minus gamma squared here. You get radius squared times sample size. And all of that is raised to this power, 2 alpha over 2 alpha plus 1. Okay, so just to be clear, 2 alpha over 2 alpha plus 1 is very standard in, standard prediction problems. It makes sense because as alpha increases, as it goes to infinity, then the eigenvalues decrease more and more quickly. And in the limit, this should look like a parametric problem. It should look like a one-dimensional problem if alpha is enormous. And if alpha is enormous, then this exponent here converges to 1. And in that case, you're getting a 1 over n rate. That's a parametric rate in statistics. That's sort of to be expected. What's more interesting is if you have, for instance, a spline kernel of order 1, then alpha is 1, and this rate is 2/3. Okay, so let's again look at our theory and compare it to what happens empirically. All right, so what am I doing here? I'm constructing 2 examples. I'm using a Walsh basis that Yaqi constructed. We're looking either at a polynomial decay in eigenvalues like this. So that's what a first order spline kernel with a uniform distribution would see. Or we're looking at a exponential decay in the eigenvalues. That's what a Gaussian kernel with the uniform distribution on compact domain, that's what you would see. And I'm plotting versus sample size. I'm plotting the mean squared error of the method with lambda n being chosen optimally according to the theory. And these points are averages of many trials, and the solid lines are what the theory predicts. Okay, so it's extremely accurate. The only thing that we're cheating on here is there's an unknown constant. We don't know the right constant that this curve should be multiplied by, but that's the only thing. It's not like we're fitting the theory. The theory is coming from this slide, and the only thing I'm tweaking is this, because we don't know that accurately. Okay, so that's in some ways not surprising. Just to be clear, the paper that I mentioned by this nice paper by Faramond et al. Actually gives similar rates with these kinds of exponents using metric entropy conditions, not kernel eigenvalues, sort of more restrictive soup norm metric entropy conditions. It's more general, of course, it's not just kernels. But that paper doesn't really handle the things like the Bellman variance properly or the discount properly. So there's sharpening in those terms. So let me show you another construction that we can do, which sort of tells you that what we're predicting based on how this Bellman error term behaves, right? That Bellman error, that's an instance dependent thing. It depends on the fixed point that you're estimating. So we can construct problems of F stars that are either easy or hard, and we can apply the method to these different F stars and study the behavior of the algorithm and compare it to theory. Okay, so what we do in the paper is we construct one ensemble that's easy. So why is it easy? Well, it's sets of problems for which the kernel LSTD fixed point, for which this Bellman residual is of order 1, and the Hilbert radius is of order 1. And what our theory predicts is that if you look at the scaling in horizon, it should scale in a very particular way with a certain exponent that, again, depends on alpha. And that's what I'm plotting here. For this easy ensemble, alpha here, I think, was 1.2. This is the theoretical prediction, and these are empirical trials with error bars. We also construct a hard example where these quantities scale, these blow up as you change the discount factor. Okay, so that's a much harder problem in some sense. And our theory predicts a much larger scaling in the horizon, H. And this is our theoretical prediction here, along with error bars. You can see the fit is not quite as good here. The fluctuations are getting very, very large in the error bars. Probably we could sharpen this I think there's some errors in the fit for small values of effective horizon, but generally speaking, the theory is tracking quite well quantitatively what we see in practice with constructed ensembles. Okay, and just to be clear, if you take alpha to infinity in this exponent, this goes to 3. Okay, so when you have a very smooth problem, like a parametric problem, then you will see a cubic scaling in horizon, and that's been seen a lot in past work on LSTD, for instance. But you can certainly get much milder scalings, is what this is telling us. Okay, so I'm just keeping track of my time, and I'm at 50 minutes. You asked me to keep it to 50 minutes. I can sort of truncate early, or what would you guys like to do? I'm open.
I think we're around, like, we're gonna stick around like for however long you wanna go. Fine. Don't need to rush it. Okay, well, don't take that too seriously, but
yeah, no, I understand. Yeah, I don't want to keep everyone too long. I'll talk for maybe 10 more minutes if that's okay.
Yeah,
just because we had a few questions and
yeah, absolutely.
Okay, so all right, so the natural thing you might ask is the following. Okay, so you're proving some upper bounds for a particular non-parametric estimator, and your theory seems to be sharp in the sense that, you know, empirically your theory is predicting what's happening. But of course, in practice, maybe there's a better estimator than what we proposed. So the complementary question to address is, can you give lower bounds that are in some sense matching, and lower bounds that hold for any estimator? And any estimator here means anything that uses the data in some measurable way. Okay, so what we're doing here is we're doing a minimax analysis. So what it means, it's minimax, we have a soup, we have a worst case over choices of problems, and F star is some possible kernel LSTD fixed point in some family that we construct, and then we look for a best case over all possible estimators. Okay, so it could be something very computationally efficient if you wanted it to be. The only restriction is that it just uses the data that's given. So we have a partial result here. So remember, our upper bound is of the form r squared delta n squared. Delta n squared here is the same thing in our upper bound. Our result is partial in that what we can handle is we can handle any discount factor. We can handle any eigenvalue sequence, but we cannot handle any Hilbert radius and any Bellman error. It just gets quite complicated to deal with all of these things simultaneously. So what we did is we give lower bounds over 2 regimes, sort of the easy regime where these things are order 1, and the hard regime where these are order 1 over 1 minus gamma. That sort of spans an interesting spectrum of problems. And what this result says is that basically up to constants, you cannot do better than what we're giving you. And that again holds for any kernel, any horizon, but for particular choices of radius and Bellman error. Okay, so that's in some sense, we have, I think, a pretty good understanding of this particular special problem. But as I mentioned, there's many things that we've assumed, lots of open questions. One thing that you already asked is, we're looking at a very simple independent sampling model. We should deal with the Markovian case. That's certainly interesting, something that we're thinking about. Some other questions, sort of what I've given you is theory, but it's not super practical yet, because I'm telling you, if you magically choose lambda n in some way that depends on some things that you know and some things that you don't know, then you will get a good result. So in practice, what should you do? I suppose I could punt on this and say, oh, just cross-validate or do leave one out or something like that. But to me, that's not fully satisfying. Partially, you're wasting data. But also, I think the question of assessing the error of this method would be interesting in a data-dependent way to be able to tell you what is the error of your method. And if you could do that, if you could estimate this lambda n squared from, or sorry, this lambda n or delta n squared from data, you'd actually know what the error is. So what's known? The sample size n is known. The discount is known. The eigenvalues of the operator, just to be clear, when we implement these methods, I didn't mention this, everything is done using kernel matrices. The method is just a linear system solve in n dimensions. So its complexity is linear system solve plus order n squared kernel evaluations. So the kernel matrices have empirical eigenvalues. You can actually just plug those in directly and get all the same guarantees. What's unknown is the radius, the Hilbert radius, and this Bellman error. So I think it's quite interesting to figure out, can you estimate these quantities in a data-dependent way and plug back in and still get guarantees? We know how to do that already for tabular problems, but of course this is more interesting, more general. Another issue I think here is these bounds are somewhat instance dependent because they depend on things like the stationary distribution of your problem. They depend on the Bellman fluctuations, but they're not really particularly careful about controlling the mixing properties of this transition. They basically just use a worst case bound for it. Basically that lower bound that I mentioned earlier on that interesting operator, which is the covariance operator minus gamma times the cross covariance. I think there's something more that could be done there. Maybe just sort of highlighting, so for LSTD, we have a much more precise result, just so you understand what I'm talking about. Let me just highlight this just to wrap up. So if you run LSTD with a d-dimensional feature vector, this is a result that applies to an algorithm that runs the ordinary TD updates. It runs them with an aggressive step size so that the algorithm moves quickly, but then it does what's known as Polyak-Rupert averaging. This is a standard thing that people apply in stochastic approximation. But what we show is that the error in estimating the true value function can be upper bounded in terms of an estimation error and some number, an approximation factor times the approximation error. And everything here is completely sharp. There's nothing that can be improved in this result. Let me just sort of highlight, how does the mixing enter? It enters in the natural way. So what is this? This is the cross covariance operator on state and next state pairs under your feature map. That's a d-dimensional matrix. You renormalize it by the covariance matrix of your features to make it a correlation matrix. And then you get I minus gamma m. Okay, so this is a generalization. In tabular problems, you see I p, where p is the sorry, I just lost connection. Can you still hear me?
Yep.
Okay, thanks. Yeah, so this is a generalization of I minus gamma p, but for LSTD. Okay, so our result in the non-parametric setting is not as sharp. I don't really know how to do it. It's kind of complicated, although one can sort of imagine how it might be done. Let me wrap up there. There's other things I could say, but I think just to keep us on time, let me just summarize. So in this talk, I did something pretty simple, just looking at a careful analysis of a standard estimator, kernel-based LSTD. Again, with a simple sampling model, but I think we have a pretty good understanding of it. Lots of open questions here. We mentioned Markovian data, the instance-dependent issues. I think there's more to be understood in approximation estimation trade-offs. And it's interesting to think about what happens when you start plugging in this kind of method into other RL things like policy optimization or like an actor-critic method using kernels as the critic. So these are all things that we're thinking about. So a few preprints and papers, and happy to take any other questions that there might be.
Thanks.
Shall I ask a question?
Hi, Sean.
Hi, Martin. I feel so bad. I didn't look at the time. My calendar said 2 p.m. and I thought 2 p.m. and I showed up on time. Oh my God. Well, I'm going to enjoy reading your paper. Do you think there's really any hope for Markovian data? I mean, you've been hearing me preaching for years about a simple example like an MM1Q, and you can't get bounds for just simulating the mean. They don't exist. I mean, there's no like Huftian inequality. There's nothing. And any skip-free Markov chain, you have that problem. And so, and then of course you could say, well, I'll stick to finite state spaces, but then you look at like Peter Glynn's work, and they're hopeless. The generalizations of Huftian's inequality for Markov chains gives you results that are so meaninglessly conservative. They're worst case sort of bounds. So what hope is there?
Maybe I'm not as pessimistic about like tail bounds for Markov processes. Like if you have some kind of mixing condition.
Like take a MM1Q, it's geometrically ergodic, it's reversible, it's got every feature in the world. And if you try to estimate the sample pattern, the mean just through Monte Carlo, it doesn't satisfy. I mean, you can prove that actually you don't get anything like the bounds for tail, probability of exceeding the mean. They're nothing like it.
I'll have to think more deeply about your question. Yeah, I think I agree that yes, there will be cases where it's going to be too hard to say anything, but certainly with Markovian data and LSTD, we have pretty sharp results that separate the contributions to the variance that come either from mixing related issues relative to just things you would have seen in a non-Markovian setting. That is a special case, has lots of structure. So I guess I agree with your point. Maybe I'm not as pessimistic, but maybe I'm less ambitious in the class of problems that I would be willing to have a result for. So.
Okay.
I mean, on the positive side with Markovian data, you can start doing things that you cannot do with my sampling model, right? Like TD lambda, for instance, is only possible because you can get unbiased estimates of higher order transition operators, right? So there's an additional degree of freedom that people are aware of and do exploit, but that's sort of maybe a positive message for trajectories. Yeah.
The number of tools you have. And there is one trick that sort of, so way back when people try to look at large deviations for simulating Markov chains, they look at these pin simulators. And Yannis Kondianis and I followed up on that. So if you sort of conditioned on the Markov chain not being too far away, you can get sharper bounds. So that's something. So there might be tricks like that. It might be useful in the future here too.
Okay. How about I'll send you a preprint once it's ready of something that we have on Markovian data, and then I'd be happy to hear your thoughts and references to things that we should be thinking about.
Great.
Yeah. Thanks, Sean. I appreciate it.
I have a small question maybe that I can jump on quickly. So at the beginning of the talk, you mentioned the result by Cho and Titikles. And I can't recall whether that result applies to policy evaluation, because I said that it was done in the context of optimal value functions, but it may well apply, but I just don't remember.
Sorry, Chaba, I missed which result were you referring to at the beginning of the talk?
Show and typically at the beginning when you mentioned that curse of dimensions
right.
may apply.
Yes. So if my memory is correct, I reread the Rust paper recently. So
okay.
So where are we?
Trust
yeah, you're talking about.
Yeah.
So you're talking about this. Yeah, I have to revisit that. I haven't read that in a while, but this one is certainly, Rust is looking at this problem and he assumes that this is known, but he doesn't sample from this. He samples from something like a uniform distribution on a compact domain. He constructs a different Monte Carlo approximation. It's something that you cannot do in RL. And the problem is in many ways much easier. So yeah, he does not sample from this. What he does is sample uniform and then he evaluates numerically.
That's right. Yeah.
So, which you can do when you know it.
I think the main difference though between the model and of Rust and Choice-Typically is not even that, but that Rust allows extra access to the model when it needs to produce a value estimate. So it's like an online access or local access or something like that, as opposed to Duan this paper was about global access, that like you access the model to computations for a while and then you can't, and you have to produce the value function that is approximately correct everywhere. It's like much harder.
I see. So,
but I'm the question was whether the Choice-Typically it might well apply to policy evaluation. I was wondering whether the max played a role in that result.
Yeah, this is a good point. I should go back and look. It's been a while since I've read the Choice-Typically, so.
I wouldn't be surprised if the max didn't play any role, even if it's there in their paper.
The max certainly does complicate one's life in many settings. So
yeah, but like for a lower bound, it's like it would be even a stronger result, right? If we had it without the max.
Agreed.
Anyways.
I mean, there are cases, right, in which, for tabular Q learning, it's not like tabular Q is any harder than tabular policy evaluation. The intrinsic difficulty ends up being the same for many cases. So max complicates a lot of upper bounds, but I don't know if it, from a lower bound point of view, always makes the problem fundamentally harder. So.
Okay. So you mentioned at the end of the talk that I think for the finite dimensional case, you have some ways of measuring this bellman error. I can believe that. I think that they're just like, well, wait. So even the bellman error, it was with respect to f star, which is unknown. So you would need to construct an estimator. But I guess maybe the finite dimensional case is just like everything's so fast concentrating that you can just use plugin estimators there. Is that the idea? Was that the very end?
Right. So here's the finite dimensional case. Right. So this is just a d-dimensional matrix. So I guess what you're asking is, this is unknown, but you can imagine doing plugins where you use data to replace this with some m hat. I think we might have lost Chaba, or can you guys still hear me? Some people are moving, so yeah.
We can hear you. I think, yeah, maybe Java has dropped a little bit.
Should I wait?
Oh,
he's
he
back.
moved.
Oh, he's
yeah.
back.
He disrupted the meditation.
I don't know what's going on. I'm back.
Yeah, so Chaba, for tabular problems, for instance, we know how to do plugin exactly. I don't think we know how to do it in general for LSTD, and I don't know how to do it in a non-parametric setting. But yeah, what you would like is you replace M with some M hat that's purely data dependent.
Right.
You replace the covariance with some cov hat. So everything data dependent. And then this would be very useful because you can evaluate the bound and you could terminate early. You could sort of imagine a stopping criterion for the algorithm.
I see. So this is basically what you meant. Okay, fine. Yeah.
Yes.
For the non-parametric case, I think that this problem is related to estimating how well you're doing, like what's the base error rate. And yeah, I said that there were some hardness results about that.
You're saying because, well, it's not classification, so it's not base error per se, but it's, you're saying it's difficult to estimate like, the mean squared error of an estimator.
Yeah, because like, you want to know it for the regression function. Regression function is not known. And if you are in a reasonably complex situation, like maybe it's related to model selection, and like if you have a reasonably rich model class, then it becomes impossible to simultaneously know how well you're doing and doing well.
I agree. I think the thing that worries me, so the two unknown things are this and this. The Bellman fluctuations I can see doing by some plugin because it's, you know, it's some average. It worries me to estimate the Hilbert radius because the Hilbert radius is sort of, you know, the eigenvalues are decreasing and the Hilbert norm is like 1 over the eigenvalues. It's going to get very unstable in parts. I don't know about that. You could be right that they're hardness results. That's a good cautionary message for us to think about moving forward.
Okay.
But I guess in general, I think this problem of trying to produce bounds that, like these bounds are clearly sharp enough, you know, when they're computed with exact quantities to be practically informative. And so if you could actually make them fully data dependent, then they're actually useful. So we somehow closed a little bit of a gap between, you know, theory and practice. That's what I'm particularly excited about these days. So
yeah, it's a very worthwhile activity for sure. It's very cool, actually.
So I had one question. So I had one question regarding the choice of lambda, that you have this limitation in your bound that so that lambda should be chosen appropriately large enough. So do you think that this actually captures a real effect, that if you choose lambda to be too small, then does the algorithm actually misbehave really badly?
I'm pretty sure it does, because if you analyze just a kernel ridge regression estimator, like this static prediction kernel method, you can do a different analysis that basically has two terms, one which actually blows up in lambda. So I'm pretty sure it would blow up. I guess in our analysis, there was a lot going on. I didn't see how to do that, so we didn't manage to do it in the end. I mean, maybe a few comments about the analysis, just to go back to the question I think that Chaba answered. What's sort of, okay, what is unusual here relative to a static prediction problem? Well, the signal to noise ratio is interesting, but the choice of lambda n is interesting because you have this weird 1 minus gamma. That does not happen in a static prediction problem. Well, static prediction is gamma equals 0. In static prediction, the rule is always set lambda n to be proportional to the mean squared error that you expect to see. But here you're setting lambda n to be considerably smaller, and it's complicated, and it has, the reason this happens is exactly because of this weird function that Chaba was asking about very early in the talk. Right? We actually analyze, we do a lot of the empirical process with this weird function, which is not quite a norm. Well, you can sort of make it into a norm by symmetrizing and so on, but somehow this is the right thing in an RL problem, in a sort of, you know, two-step RL problem. And it's only at the end that we use this bound. What we should do, if you wanted an instance-dependent bound, is you should actually start dealing with an approximate inverse of this operator instead of just using this crude lower bound. But that's what we did. So yeah, the subtlety is yeah, in working with this object a fair bit. So for those of you who know the empirical process theory and analyzing these kinds of things, you have to do like peeling and concentration over function classes. And we do a lot of it with this instead of this. It took us quite a long time to realize that we kept doing it with something else, and then you get suboptimal horizon dependence. And then we realized, oh, you just have to work with this object. That's fundamental. So hope that clarifies.
It does, and maybe the regularization, like the scaling with the 1 minus gamma, is also can be seen from this inequality, right?
That's a good point, actually. Yeah. Yeah, that's a very good point, right? Because sort of the scaling of delta, this is going to be at the scaling of delta squared. So you want lambda to be on the same scale as this object. So that is the correct intuition for why that scaling happens.
Yeah. I had a quick question just related to this operator.
Yes.
Is it fair to say that sort of the spectrum of this operator is somehow related to mixing properties of the process?
Definitely, yes. And this lower bound is very crude because it acts like your process has like a non-mixing sort of deterministic component. So it's exactly mixing, and it's mixing not in the original space, it's mixing in, you know, the space of functions on the Hilbert space. So in LSTD, right, you should be looking at mixing of the feature vectors, not mixing of the original Markov chain. Makes sense, of course, right? Because you're working in that space. I think that's very interesting to think about. This is very crude, and if you want a real instance-dependent analysis, you have to do better here. I tried to do better, but there's a lot of moving pieces, so you know you got to choose your battles. Yeah, but I think it's very interesting to think about spectral properties of chains and actually how it interacts with the, you know, the Hilbert space is a choice that you can make. Like even in LSTD, the feature space is a choice you can make. And in making that choice, you will influence mixing in the feature space. And that's something you should think about because that's going to affect both the estimation and the approximation error. So in designing, you know, function approximators, this is something that, you know, one should be thinking about because clearly the bounds care about it.
The wide question. This is in a way on policy. So how much of this analysis depends on that we use a stationary distribution of the chain?
A fair bit. Like for instance, this bound right here requires stationarity to prove. It's just Cauchy-Schwarz, but you need stationarity. I can give you sort of a weasel answer to that question, which would be if it was, well, if I'd analyzed the Markovian case, then I would just be weaselly and wait for it to be near stationary and then bound the distance to that. But that's not really a satisfying answer. I think the deeper question, which was what we initially started with, is to actually understand this kind of method in off policy. Because my collaborators Yaqi and Mengdi actually, as probably many of you know, have an earlier paper about off-policy forms of LSTD. So our motivation was actually to think about off-policy kernel, but it got complicated enough that we backed off to on-policy. But that's a very interesting question to think about as well. So that's, I think, the non-Weasley answer to your question.
Cool. All right, something for the future.
Well, there's lots of things for the future. So many interesting questions in this area.
Yeah, we agree.
Are we still being recorded or can we speak freely now?
Oh, let's stop the recordings.
No, I'm not going to change my behavior.
stopped, I think.
It doesn't really matter to me that much, but
yeah, sure. But what's on your mind?
What's on my mind?
Yeah.
In terms of work or in terms of not work?
Yeah. Either way.
I think I've spoken enough.
Like, okay.
Should let others speak. I'm happy to hear.
Yeah.
So is your Alberta deep mined? Is it some sort of mixture distribution? And what are the weights on the mixture distribution?
3/4 to 1/4 to deep mind.
3/4. You're more often in London then?
Yeah. No, actually, there is an office in Edmonton as well. So I can just like stay in Edmonton and be happy with my proportionate. Yeah.
I see. That's nice.
Yeah.
By the way, Yaqi is shown while she's here.
Yeah.
She opened her mic, so
yeah, just so that you stop the recording. So yeah, it's time to show.
I see. So the stopped recording does bring out some people out of the woodwork.
Good.
Yeah, it was fun to work with Yaqi, and we actually just met for the first time in person a week and a half ago. So, I mean, the pandemic is horrible, but on the other hand, it's just made collaboration or made us adopt this new mode of collaboration where it's just kind of electronic and relatively seamless. So
yeah, that's pretty cool. I saw it happening quite a bit, so it's cool.
I should put in a plug that Florida is hiring in machine learning and quote unquote AI and RL, and we're gonna you can come and help me get rid of our governor. Just.
Is that your recruiting message, Sean?
Yes. Come help fight with these groups.
That's the lamest recruiting speech I've ever heard. Is that gonna work?
Yeah, the whole world is, but yeah, the governor's nuts. I'm sorry. Yeah.
My wife had some collaborators in Florida, and she said that at some point they were forced to go into work and then forced not to wear masks or something like really crazy.
Well, this is the crazy stuff Ron DeSantis was saying to us, yeah. And of course we didn't listen to him. And he's nuts. I mean, he's trying to sue the elementary schools, because they were trying to get the kids to wear masks. he's crazy. I mean, he's like a little trumpet.
God bless America.
Oh yes. Oh yeah.
As a Canadian, I always have sort of a strange love-hate relationship with the U.S.
I consider myself part Canadian after 5 years in Montreal. It was beautiful 5 years. Just yeah.
So Yaqi, how did you end up choosing this character?
Sorry, I choose this character.
That's on the slide. We were told that you chose the pig character. Yeah, that one.
Oh yeah.
It's very cute.
Thank you. Yeah, so it was shown by Hannah, like Martin's doctor.
You don't know Peppa Pig though, Chubba?
Yeah,
No.
Peppa Pig is a British cartoon, very popular among kids. So maybe your kids are old enough that you escaped this?
Yeah, they grew up in Hungary, and by the time we moved there, yeah, it was too late, I think, for these cartoons. So maybe it's my grandkids. I will have a second chance.
I mean, as children's shows go, I think Peppa Pig is one of the better ones, personally.
Okay.
Yeah.
I mean, it's sort of quasi-educational. It's not especially annoying.
Okay.
So
I see. It's for kids of what age?
I don't know, 2, 3 kind of age, like
2, 3. Okay. I do have grandson who is of that age, so strange that I haven't seen these shows. But of course, it's pandemic time, so I'm missing out a lot.
I think Peppa Pig was more popular maybe 5 years ago. It could have waned in popularity.
Yeah.
It's hard to sort of track these things, but
I see some show with some girl and some cats. Kitty cat, something. That's fun too. Anyway.
So what are people here most excited about or working on, etc.?
I feel that I spoke so much. I can tell you very briefly, but we've been working on trying to figure out query complexity of learning with linear function approximation, or like in the presence of a simulator of like just, figuring out a good policy. When you have linear function approximation and the linear function approximation only helps you to approximate the optimal value function, let it be the state value function or the action value function. And it's been a lot of fun. And there are still quite a few interesting questions. So it depends.
So you're talking about realizability and whether only optimal policy or
like,
all.
It's like even under realizability, this problem can be hard, depending on whether you have a lot of actions. So it turns out that if the number of actions scales with the dimension of the features and the horizon simultaneously, so scales is the minimum of the two, then in a polynomial fashion, then this problem can already be hard, exponentially hard in these parameters. So it's like blows up. Bad news, but it's been fun.
Yeah, so I guess your group had some earlier results with finite action spaces, like bounded.
Wait, like here it's like completely discrete. It's like you have finitely many actions.
But order one, not allowed to scale.
Oh yeah, the order one, like that case, you can have polyquery complexity. We don't know about the computation complexity. So just two actions, Q sterilizable. You go with your simulator, whichever access model you want to use. Is it polynomially efficient or not? We know it's very efficient.
Yeah, no, Andrea Zanetti is a postdoc here now, so I've been talking to him a lot, and he's been telling me all these crazy gaps of this type that you're mentioning. It is pretty surprising, these gaps.
It's it gets pretty crazy very quick, and so it's been one pretty fun project.
It feels like some new sort of graded assumptions are needed to kind of close the gaps between being able to do everything and being able to do nothing.
Yeah, but I guess here this is really the hardcore approach, because you're not making any strong assumptions about the use of the features. Like you could assume things like, oh, the features can be used to approximate the value functions of all the policies or something like that, right? Like there are all these alternative assumptions about what can you use the features for. But this is the craziest in a way that the features are only good for one thing, and like you're not making any more assumptions about them, which increases the scope, of course, but then we see that things turn out quite badly. So so there are alternatives. I don't know. I think that we should also somehow do something more about the actions. Like like working with this discrete action space and the structure only comes from the features, I'm not sure that this is such a great idea, but I don't know what to do about it. Like you want to deal with large action spaces, but you need some structure. And then how do you capture that?
I mean, there's certainly cases, you know, particular applications where the action space is very structured somehow, and there's likely to be some smoothness results between nearby actions and the behavior of the transition functions and so on. So,
yeah.
But it feels like you'd have to somehow immerse yourself and figure out what are interesting classes of such assumptions under which you study things. So,
which is the hard part, or one aspect of the hard part.
Agreed.
It's hard in a way because it's like everyone has their own favorite things, right? So how do you convince other people that your way of thinking about these things is the best? Wow, maybe you are.
Academics are like herding cats. They all have independent ideas and directions, but I mean, that's part of our strength.
Yeah.
So.
Yeah. That's fine. It is just that sometimes it's, like if people start to agree that something is interesting, then it's maybe more exciting to work on it. So Sean, what's new with you?
Or me?
Yeah.
Actually, you actually made me think. I mean, when I was a grad student and assistant professor, control strength was sort of like RL, that there was like a couple of gods, like Carl Ostrom on the adaptive control side and George Sims on robust control, and then their followers. But there was a cohesive tribes, two tribes. And then there's John Tsitsiklis doing this beautiful work in RL. We all ignored him. but the community was great, and all these beautiful things came out of it. And what killed control was people getting into applications because people became siloed. And so even though probably there was more contributions to society when control was destroyed, because people started looking off for impact, it just the community was crushed, completely destroyed. You know, it's really funny. And RL is as important as it is to find structure and develop RL within certain application areas. Those people that go off and are heroes and solve a big problem in power systems, say using RL methods, nobody in RL will care about them. You know, they'll just be isolated dots. You know, because it takes a lot of time to really get a successful application of any control technique. So it's like it's hard. Is it? You know what I mean? You want to be artists and be in a community of artists, and then you want to have impact in applications. It's not. You can't be both. It seems. You know, it's very hard. Yeah, that's right. You can be so excited that you found the special geometry in power systems that you could exploit to get an RL algorithm, and you bring it back all excited to an RL talk, and everybody goes, "Who gives a damn?" You know, so you have nobody to share the excitement with. Yeah, so it's funny.
Sean, obviously you know better than me, but were there not other factors in the sort of, you know, decline in control in that period of time? Like my impression was a lot of the sort of basic problems had been solved.
Oh yeah.
And then it was just getting kind of technical and hard, and there was nothing really you could solve anymore somehow. Is that an incorrect impression?
I think that both are true, but the siloing was huge. I mean, the fact that there'd be a little, you know, the CDC suddenly, there'd be a special session on, I don't know, on electrostatic motors. There was nobody except for those 10 people who cared. You know, the field became very fragmented.
Interesting. Interesting.
Yeah. And the power has been a disaster in control for reasons I won't gossip about. It's just because I will say it. Everybody's obsessed with real-time prices, and they think that's going to solve all the problems. So you have entire sessions on people pretending they're Milton Friedman, just saying that you'll have price signals and everyone's going to be controlled by their self-interest, free market. So
it sounds like
it's not a joke. It's a nightmare.
You have a conservative governor, and then in power systems, you're surrounded by Milton Friedman acolytes.
They're crazy. It's a crazy field. It is. It's a fucking crazy field. I mean, it's amazing. I mean, you can't believe Federal Energy Regulatory Commission, the things they say. They're loony. About, can you imagine your power bill going up and down and you turn on and off switches, and they say, oh, it'll be automated. So you mean the prices are going to go up and down and I don't even have control? So yeah, I mean, the world's nuts. So, and what else? I mean, so yeah, so it's people that are doing abstract nonsense where a community is possible, So Johnson Sickler is really pissed at the people who are still doing consensus. And it is annoying, but at least there's community and ideas do pop out because it's a big enough critical mass of people who can talk to each other. And online optimization is another one where it seems like it was done, but it's compelling enough, it creates a community and ideas do come out. So it's strange, it's the best way to foster a research community is really tricky. Yeah.
But for instance, with consensus, do you think that there's actually new interesting things coming out? I mean, I haven't followed.
Luckily, that did die. I think things did. I think, and yeah.
I mean, I can understand John's irritation because there were a lot of papers that were like at best epsilon increments or at worst no increment beyond what he or somebody else had done in 1988 or something like that. So it's not scholarly.
Yeah, I don't really know because I try to keep away from it myself. But I mean, it's just that in every one of these, these when you get this flocking and there's a research community, of course there's insane inefficiencies, but what's our goal? Our goal is to get excited about each other's work and to train students who are going to go on and do whatever. And so you want to create, even if it's a fake topic like consensus, the creation of a community still has great value. It's strange. Try to tell that to Congress, but yeah. I know I've thought about this a lot. It's really the dynamics of scientific community is really interesting.
I think it's really funny, this whole thing, because I lived through most of my career when reinforcement learning was just like this little island that no one really cared about. No one even heard about. They didn't even want to hear about.
Yeah.
And it's like now it's blown up. Is it better? I don't know. I'm certainly very, very happy that I see new faces here who are contributing in various ways. So that's great.
Yeah.
So I think, like you can benefit from some momentum, some excitement. I don't know, like this control. Yeah, maybe you just like have to add the learning component and admit that, okay, like we need to do that. Well, we called it adaptive control before, but we can't do that anymore. We have to call it machine learning, and then it's all good. Then the students want to join.
Yep. Well, I've always followed my course catalog.
AI.
Every 20 years, I've stuck that in my stochastic control description. Yeah. They see learning, they get excited. Yeah.
Yeah. All right. Anyways, I gotta go. It was fun.
All right.
Thanks.
Thanks, everybody. That was fun.
Good chat. See you.
Thanks for the talk. Bye.
Kara, can you add me to the mailing list? I don't think I've been receiving all